In this video, we're going to look at how the MOSFET differential pair responds to difference mode input. That is, a differential input signal. To do that, we'll start with the simplest case, where we have one of our transistors Q2 with its gate terminal connected directly to ground, whilst the other transistor Q1 has its gate terminal connected to a voltage source VID. This provides our differential input as the difference between VID and ground. So we're interested in how this circuit responds to that input. So what would the output be? So we'll take that as the differential output between the two drain voltages, VD1 and VD2. So Vout equals VD2 minus VD1. So let's first take the case where VID is positive. So we can see that this will mean that our VGS1 will be greater than VGS2. So this is the drop from the gate to source on each of the transistors. So we can see this is true because they have a common source terminal, and Q2 has a gate voltage of 0, whilst Q1 has a gate voltage of VID, which we said is now more than 0. So from our basic transistor functionality, we know that this will result in ID1 being greater than ID2. So that is the current flowing into the drain terminal. So how does this affect our output? Well, we can easily come up with an expression for VD1 and VD2. So that is VD1 is going to be equal to VDD minus ID1 RD, whereas VD2 is going to be equal to VDD minus ID2 RD. So by plugging these equations into our expression for Vout, we can see that Vout is going to equal minus ID2 RD plus ID1 RD. So it's quite simple from here to see that if our VID is more than 0, we have our ID1 is more than ID2. If ID1 is greater than ID2, then our output will be positive. Now what about the case when VID is less than 0? Well, for the same analysis, we can tell that VGS1 will now be less than VGS2. This means that ID1 will be less than ID2. So again, plugging that into our equation for Vout, we can see that in that case, the differential output will be negative. So in conclusion, we can say that the differential pair circuit responds to a differential input by providing a differential output. So a positive VID will provide a positive differential output, a negative VID will provide a negative differential output. So this is in contrast to the common mode input, which we looked at in a previous video, in that case, with a common mode voltage coming into both terminals, we saw that there was 0 at the differential output. So we know that by changing our input differential voltage VID, we can effectively manipulate how much of the total available current I is passed through either transistor Q1 or Q2. But at some point, we can reach a voltage VID at which all of the current will pass through only one of the transistors. So this will limit our range in input differential voltage. So here we will start by looking at the maximum VID. So this is the case when ID1 is equal to I and ID2 is equal to 0. And at the point where ID2 equals 0, we know that VGS2 will equal the threshold voltage VT. So there is no overdrive in the voltage in the second transistor, because that would cause current to flow. So to work out the point at which ID1 equals I, we can use our transistor in saturation equation. So we know that ID1, which is equal in this case to I, equals 1/2 of the process transconductance parameter times the width over the length times VGS1 minus VT squared. So we can rearrange that equation to get it in terms of VGS. So that would lead to VGS1 equal to VT plus 2 over I Kn W over L, all square rooted. Now we can simplify this expression with a little trick, because we know from our common mode analysis that under the common mode conditions, where we actually have this total current split evenly between the two transistors, we can say that the overdrive voltage VOV is equal to I divided by Kn W over L square root. So that allows us to express VGS1 as VT plus root 2 times the overdrive voltage under the common mode conditions. So we want to know, to get this expression in terms of VID, and we know from our circuit that VID is equal to VG1. So let's split up our term here. So VGS1 can also be written as VG1 minus VS, which is equal to VT plus root 2 VOV. Now we also know that VGS2, from our initial conditions, we know that VGS2 is equal to VG2 minus VS, which equals VT. And as we know that VG2 is connected to ground, we can say that VT is equal to minus VS. So substituting that into the above equation will give us VGS1 is equal to VG1 plus VT, which is equal to VT plus root 2 times the overdrive voltage. So we can see here that our VT terms can cancel out, leaving VG1, which is in this case equal to VID equal to root 2 times VOV. So that is the expression for VID under the conditions in which all of the available current is passed through Q1. So we can do a very similar analysis to find the lower limit of VID as well, and that will come out to be the negative root 2 times VOV. So now we have our limits of differential input voltage.